Hello. Now we're going to talk about the theory behind today's lab experiment. Are you ready?
Yeah. Come on.
I knew you were. Quiet, Darren. That's my son being the cameraman now. I was talking to him. Are you ready? The guy's watching this video. I hope so. Okay, now there's a lot of these. You can see this on the internet a lot of places too, and it's not that hard. But the important thing to do, which I did at least once so far, is getting the sign. You got to keep the signs right. All right. Now this is what we have. We have mass 1, which is equivalent to the cart that you're going to have, and mass 2, which is equivalent to the hanging weight that you're going to have. All right. Now we know from Newton's second law that the sum of the forces is equal to ma. General formula. Okay, now that's true in both the x direction and in the y direction because forces are vectors. Alright? Now, so let's take a look at this thing here. Let's look at mass 2. Okay? What are the forces on it? Well, there's a force going up called tension, and there's a force going down called gravity. Okay? Now some people don't understand what this tension is. Now just imagine this, that instead of a mass hanging down there, it's you. There's a rope around your neck. Don't you think you would feel some tension pulling you up while your own weight pulled you down? I think you would. We're not going to try that though. And I don't suggest you try it at home either. Okay, so we have the force of gravity going down and the tension going up. So we can know that... Alright, now here's the tricky part, so pay attention. Are you paying attention? The gravitational force, we know that's going to be m2g minus the tension. It's going to be equal to m2a2. Now how did we get this sign here? Why isn't it t minus mg? Well, we know that the gravitational force is going to be heavier than the tension, otherwise it would go up. Not heavier, higher. So we want to keep it so that this is going to be positive, this is going to be positive, they're both going that way. Okay? Makes sense? I think it does. What do you think, Derek?
Sure.
Okay. Alright. Remember, he got an 85 on the quiz for Lab 1, so he must know something about physics or just be good at guessing. Alright. So now for the second one, that's just in the y direction. It turns out we don't really care about going in the x direction on mass 2, trust me. Now on this one here, mass 1, if we draw a picture of it, we've got forces in the x direction. We've got a force T pulling it. And now I think you can see that that tension is going to be the same going this direction as that direction. They're going to cancel. They would cancel out, right? Because the amount that this is being pulling down is the same amount it's pulling on that. All the pulley's doing is just changing the direction. Okay? So we have the tension going that way. And we're going to have a frictional force going this way. That's going to be dragging you down, man. It's such a bummer. Alright? And then we're going to have, well, we're going to have the gravitational force. This is M1. So this is going to be M1G, right? And since it's true that the cart, or the block of wood here, isn't actually going down, there must be something holding it up. We call that the normal force. That's opposed to the abnormal force. We don't want to have any abnormal forces here. That's a young Frankenstein reference. If you don't get it, I'm sorry, you're just culturally inept. Alright, so now what we can say is that in the y direction, alright, we know that the sum of the forces in the y direction is going to be equal to ma. In this case, the acceleration in the y direction is 0, so we can just say that n equals m1g. Alright? And the reason for that again is because n minus m1g equals m1 times the acceleration in the y direction, which is 0. Yeah, you got it. So N is equal to m1g. Now, the acceleration of this guy, he's going to be accelerating this way. And the tension's going to be pulling him that way. Okay? Follow me so far? You follow me, Darren?
Yeah.
Alright, so everybody's following here. So what we can say here is that the tension which is that way, minus the frictional force, okay, is going to be equal to M1, that's it, A1. Alright, well what does that do for us? Well, we don't really know, or in fact we don't really care what the tension is. We're just trying to find out usually masses or accelerations. Now, I mean, who cares what the tension on the rope is? I guess the rope does, but that's about it. And your neck would care if it was your neck there, but we're not going to use your neck this time. Maybe next time. So let's solve both of these for the tension. Alright? So in this case, we're going to get, we put the tension over there, and we get that the tension is equal to M2 times G minus A2. That's easy enough. And in this case, we're going to get just that T is equal to M1 A1 plus the frictional force. That's easy enough too. We can set these two equal, and we end up with M2 G minus A2 is equal to M1 A1 plus the frictional force. Okay, now we've eliminated the tension, but we still have all these terms we can't get rid of. You know, we got to figure out some way to get rid of some more terms. Well, here's the thing: is this rope that's holding these things together? It's not getting any longer or shorter. It's staying the same length. So the acceleration of this one going down, the magnitude of it has to be the same as the acceleration of this object going to the left. Okay, so we're just going to call that A instead. So let's just write this as M2 G minus A equals M1 A. That's an M, by the way. Make sure that's an M. Plus the frictional force. All right. So now we're really down to just one problem here. What do we do about this frictional force? Well, that's a good question. What do we do about it? Well, as it turns out, the frictional force is equal to mu, which is a property of the surface, times the normal force. Now, since it's flat, we know that the normal force is equal to m1g, so we can say that the frictional force is equal to mu m1g. That was easy enough. We can put that over there. And then we have that m2 g minus a is equal to m1 a plus, that should be a capital M, mu m, gotta make sure those are clear, that's an M and that's a mu, 1 G. Okay, now in your pre-lab you have to solve this for acceleration. So I'm not going to do that because in the lab you need to solve it for M1, which is the equivalent of M star in your lab. So let's solve it for M1. Well, we can say M1 A plus mu G. This is going to stay the same, M2 G minus A. Alright? And then we can say that M1 is equal to M2 G minus A over A plus mu G. Okay? Now, let's think about this one for just a minute. Alright? Now, in the lab, we are going to be assuming that the frictional force is 0. Is that true? No, it's not true. But we're going to see how true it is. All right, so let's just assume for a minute that we increase mass 2. We can make it bigger and bigger and bigger. Well, then this is going to increase. All right? And in fact, the acceleration is going to increase too because it's going to pull it down faster. So this term right here, the frictional term, is going to become less and less significant. So the more mass that we add on here, if we say that this is 0, then we'd get that m1 is equal to m2 g minus a over a. We're measuring a, we know m2. We even know m1, but we're just going to use the calculation to see if we get the right answer. Now, as the acceleration in m2 increases, well, this formula becomes more and more valid. Does that make sense to you? Does it really make sense to you? I want you to think about it. As this number becomes bigger, the fact that this, whatever this number is, doesn't matter as much. Okay? So then, what we can say, let's do it the other way here. Now, if we increase m1, what does that do? Well, the whole thing is going to slow down. So this acceleration is going to become smaller and smaller and smaller. And then this number is going to become more and more significant. So in part 1 of your lab, as you're going to keep adding weight on here, and what you're going to see, or what you should see, is that as you add the weight, you should see a plot that looks like this. This is your error, your percent difference. It's going to be decreasing. Then in part 2, you're going to be adding more and more weight on. And what you're going to see is the exact opposite. As you add more and more weight onto the cart, the frictional, this is going to go up like that. Now, what do you do if you don't get a plot that looks like that? It's your own damn fault. It's because you got lousy data. Actually, it's not your fault. It's your lab partner's fault, isn't it? I knew it. Yep, it's your lab partner's fault. So what should you do? Well, let's take a look. What if your data looks like, instead of looking like this for part 2, what if it looks like this? What do you think you should do? Well, you retake this point right here, and then maybe you'll get something that looks like that. All right, what if you get data on the first part that looks like that? Well, then you retake this data point until it gets in there, all right? Now, sometimes people get like really good data for the first point here, and they don't have any weight hanging on here. This is a problem. This is bad. This is very, very bad. Because then they don't have any room for improvement as they add more and more weight on here. So you want to get really lousy data for the really big percent for the first one, and so you can get better and better as you add weight to the hanger. Conversely, you want to start off pretty low here so you got lots of room for what's the opposite of improvement? Do you know, Darren?
Getting worse?
Yeah, something like that.
Right now.
Well, yeah, we're all tired. It's a long day. So you see, that's how you do it. Now, a couple words about the pre-lab. If you look in your lab manual, and by the way, Sean, you left your lab manual in the lab. Yeah, you did. It's yours. I know it's yours. Okay? It's in the Lost and Found right now. You'll see at the beginning of the lab book, you'll see copies of all the pre-labs. Now there's also a copy in your lab all the way on page 37 or whatever we're on in the lab manual. Which one should you use? Well, I'll give you a clue. The one on page 37 or whatever has other stuff on the back, like instructions on how to do the lab. If you hand that in, you won't know how to do the lab maybe. So do you think that's the one you really want? I don't think so either. The ones in the front, there's copies of all the ones that pre-labs we're going to do all semester long in the front. What you want to do is you want to fill it out there. Maybe make a copy of what you did so you can remember at the end. Does that sound like a smart thing to do? I think it does. What do you think, Darren?
Yep.
All right. It's settled. It's a smart thing to do. We voted on it. And you voted with us, didn't you? So, if you use the pre-lab page from the middle of the book rather than the front of the book, here's what I'm going to do. I'm going to hold it up in class, and I'm going to read out your name and tell everybody what an idiot you are. Okay? I know you'll do the right thing now. Have a great day. See you in class. Cut.